Okay, Precal. Last time in the Wonderful World of Math, a question was asked: why does your money double every 7 years at a 10% rate? And I kind of just showed via the equation why this is the case. We were talking about exponential growth, and I essentially said if you had something of this format, well, the equation is usually written as A equals P 1 plus r to the t as a simplistic version of A equals P1 plus r over n to the n t. Okay, and so just to rehash this a little bit, P stands for the principal, and all the principal is what you initially start off with. R is the rate. N is how you cut up the rate. And T is the time. Now, it's not principal, like spelled like that. It's principal. Excuse me. And this is equal to, I guess, A, which we would call what your new amount is. Okay. So you can change the letters accordingly. P is what you start off with. R is the rate of increase. N is how you cut up the rate. Like if you're dividing by months, dividing by days, dividing by years. And T is the time, right? This is what we talked about last time. And this is commonly called the compound interest formula. Okay, so we talked a lot about that last time. I encourage you to watch the last lesson if you need to see this again, if this is confusing to you. But what we talked about last time was we saw this situation. We saw if you have let's say we get to $1 and it increases at a 10% rate, I said every 7 years your money basically doubles. Okay. So what does that mean, right? So if we're trying to write this mathematically, what we're saying is that 1 plus 1 plus 0.1 raised to the 7th should equal what? Well, it should be equal to 2. And why? Because if 1 doubles, it should be at 2. Okay, so now let's actually solve this. So what does this become? So when we put it in the calculator, we get 1.9495. And this basically means times 2. So it's not exactly, but it's pretty close. And I don't know if you recall last time, but the actual amount was a little less than twice as much. Okay? But it's approximately double, and this is why this was the case. Now, we can take this question and we can build on this. So the next question I have is at what precise rate would it take 7 years to double? Okay? So what we're saying here now is that if we have 1 plus, now we're going to say r raised to the 7th. Now I want it to be exactly 2. So the question is, how do we solve this? Well, to do this, I'm going to rewrite this as 1 plus r to the 7th equals 2. We have to get rid of the 7. So what we do is we take the 7th root. And this gives me 1 plus r equals the 7th root of 2. And then we'll subtract 1 from both sides. So this is just a typical algebra problem. So we have this. Okay, and this is our rate. Okay, now what is that exactly? Let's figure that out. So we can see when we type it into the calculator, we get a little more than 10%, roughly 10.4%. Now, this is the interesting part about all this, right? Like, if we want the precise rate, it's a pretty convoluted number, right? Also, by the way, this 2 to the 1/7 is the same thing as the 7th root, so we want to be able to convert between exponents and radicals. So hopefully that's not something new. Okay. Next up, how much exact time does it take to double your money at a 10% rate? I think I just asked that question. Oh, at what rate? Now I'm saying at what time. I see. Okay. All right. Sorry about that. I confused myself. Okay, so now let's answer this question. How much exact time does it take to double your money at a 10% rate? Okay, so now what we're saying is you got the dollar, right? You're growing at 10%. I want to know how much time it takes to double it, right? So in this one, we're going to get 1.10 raised to the t equals 2. And this is where it gets interesting, because how can I figure out what t is, right? Well, I mean, you could just graph it and kind of figure out where they cross, but without a calculator or without graphing, how could we do this? And we run into a problem here. We can't do it just based upon the basic math skills that we have thus far. What we need is something called logs. So, what is a log? So that's what we're going to talk about today. So every exponential function, I'm reading from here, every exponential function f of x equals a to the x with a greater than 1 and a not to 1 is a one-to-one function by the horizontal line test. So it has an inverse. So what does a one-to-one function mean? So if we graphed this last time and we saw anything of the, that's so ugly, I gotta do that again. Anything of the nature, just try to make it straight. There we go. Let's say it looks like this, right? Anything that looks like this passes both the vertical line test, so it's a function, but it also passes the vertical line test, okay? So the horizontal and the vertical line test. So what does that tell me? That means it has an inverse, okay? And so if it has an inverse, then what that means is, what we're saying is that the inverse is called is a log function, and we denote it as log a, okay? This is the key insight, this right here. That is essentially what a log is. So if we give you something log base a to the x equals y, we mean a to the y equals x, okay? It has a little mnemonic to memorize this. There's a little, not really mnemonic, but visual aid. You can go something like this. I call it the claw, okay? So you can go a to the y is equal to x. And I think it's a good visual tool to kind of convert between, this is called log form versus exponential. Okay. Now, let's look at what, let me make sure there's nothing down here. Okay. Let's look at examples of how this works. So given log, let's look at this first one. Given log base 10 of 10,000 equals 4, if we express the logarithmic and exponential equations in equivalent form, if we claw it, we get 10 to the 4th equals 10,000, which is true, right? Because 10 to the 4th is just a fancy way of saying 1 with 4 zeros behind it. And that would be the conversion, right? I want you to notice, too, that when we look at something like this, what a log is essentially saying, so this value here is the same thing as saying 10 to the 4th. What a log function says is that it's basically saying that when we write this number here, which is the argument of the function, with the same base, what is the exponent? The exponent is 4. That's what a log is basically saying. That's why this initial log makes perfect sense, right? So, for example, in B, this is not what the question is asking, but I want you to be clear on this. Log base 3, 81 is 3 to the 4th, right? So it's basically saying when the base matches up, what's the exponent? Well, the exponent is 4. That's why this statement is what it is, okay? Now, again, with that being said, all we have to do in this question, this is standard practice, is, again, claw it, and you'll get 3 to the 4th is 81. Okay, so again, here, they're giving us negative exponents, but that's okay. We can, so we're going in reverse, right? Here I am just living in my own world. So 2 to the negative 5th equals 1 over 32. And we're basically doing the same thing. So one thing is I can claw this. You'll notice 3 to the 81 is 4. So 3 to the 81 is 4. So we can do the same thing. So we can say log base 2, 1 over 32 is equal to negative 5. So this is one of the cool things. We can jump between the same formats doing the same thing, right? And it's just a game. It's almost like a dance move of jumping from the first to the last is equal to the middle. First to the last is equal to the middle. Okay. All right. So if we look at this question, if what I just discussed makes sense, you should know what the answer to this is, right? Because what I just said is that when the bases match up, it's the exponent. So what is this going to equal to? That's just 7. And so this is about understanding really what a log means, because once you understand, these questions become pretty straightforward. So here, how do I write 16 with a base of 4? 16 is 4 squared, so this is 2. Again, all a log is really saying is that when the bases match up, what's the exponent? So this is interesting because it's log base 15 to the 1, but we know log base 15. So again, I want to write it with a base of 15. So 15 to the what? 15 to the what exponent power is 1. Well, we know anything raised to the 0 power is 1. So this is just 0. And so a lot of times you'll see this written as a rule. A log of any base, sometimes we'll just put like a to the 1 equals 0. And that's because you can all write anything except 0 as raised to the 0. Now, so what you can see is that all we're really doing is we're playing with the exponents. So we can rewrite this as 3 to the 1/2. Now we do have a problem here because 3 to the 1/2 doesn't have a base 9. So how do we deal with this? Well, one thing you can do is you can say it's equal to something. We'll call it x. And then we can claw it. So 9 to the x equals to 3 to the 1/2. And once I write it as such, I can convert 9 to 3 squared. Raised to the x equals 3 to the 1/2, which is equivalent of saying 3 to the 2x equals 3 to the 1/2, which is equivalent of saying 2x equals 1/2. Just divide by 2. I'm going to write it's multiplied by 1/2 because it's a little easier to visualize as a fraction. And x equals 1/4. And there you have it. Okay, so can we claw? And so I guess, can we claw? Absolutely. And I guess the question is, could I go back to some of these and do the same thing? Well, absolutely. You can say that this is log to the base 15(1) equals x. Claw it. 15 to the x equals 1. When is, oh, look, it's the same thing, right? Okay, same thing over here. We could say log base 4 to the 16 equals x. Claw it. 4 to the x equals 16. 4 to the x equals 4 squared, so x is 2. Yeah, you absolutely can do that. Okay. But if you understand what a log is, then you don't have to. And this is the big point that I've been trying to stress with this course is understanding what it is that you're actually doing, right? Because once you understand what you're doing, you can manipulate it multiple ways. Okay. So here, because these bases aren't very easily to match up, let's just go ahead and say it's equal to x, and we will plot. We'll get 4 to the x equals 1 over 2. And this is interesting because they're not the same, but we can rewrite both of these as, well, 4 is 2 squared, so I'm going to write 2 to the 2x, and 1/2 is the same thing as 2 to the negative 1. So 2 to the x equals negative 1, and the reason I can make this argument is if the bases match up, then the exponents match up. Divide by 2, x is negative 1/2. Okay, more of the same. So here we have, I'm going to again say it's equal to x. Again, I'm going to plot. So 49 to the x is equal to 7. I can rewrite 49 as 7 squared. So if we have 7 to the 2x equals 7. 7 is the same thing as 7 to the 1. So now we can say since the bases are the same, the exponents are the same. 1 equals 2x. X is 1/2. So we can see the pattern more or less emerge in regard to how we want to approach this. Okay, so let's look at this next situation. So now we have 10 log base 50, and since I don't know what it's going to equal to, I'm going to go ahead and say it's equal to x. Now, what's really important to realize first off here is that if you see the word log written with just a number, it is implied that the base is 10. Okay, so we need to see that. Now, the problem is we have the log is the exponent. So what do we do here? So what we're going to do here is we earlier said we're going to take the log of both sides. Because if we take the log of both sides, I said the definition of a log is when the bases match up, it's just the exponent. So log 50 equals log x. And so if I say log 50 is equal to log x, then 50 is x. Now, once you see this, what you can do is you see that this match up. It is legit to just say that is 50. They don't technically I don't even like the term canceling out, but you can think of them as you can cross them out and you're just left with the number, insofar as the base matches with the base here. And there you have it. So it's the same question, so it's still 50. If we have this, because these match up, this is just pi. And again, if you don't believe me, you can rework it the way I did this one, and you'll see you get the same thing. Okay. All right. Express the logarithm in exponential format. So again, if we plot, we get 10 to the negative 1 equals 0.1, which is true. If we plot, we get 8 to the 2/3 is equal to 4, which is true. The cube root of 8, remember 8, this is the same thing as saying 8 to the 1/3 squared. And so 8 to the 1/3 is 2, 2 squared is 4. So it is the same thing. We can convert back. We can say log 81 to the 9 is equal to 1/2, which is true. Here we can say log base 4 of 0.125, which is 1/8, is equal to negative 3 over 2. I wrote the same thing twice. Okay, so let's see here. So this is the rule that we were talking about earlier, which is basically if you just see log x, it just means log base 10. So if that's the case, then every time you see a log 10, you count the number 1 with a bunch of zeros behind it. You just count this number of zeros. and it tells you what the answer is. Now here, this is interesting because we have 0.1. Now recall that 0.1 is the same thing as 1 over 10, which is the same thing as 10 to the negative 1. So if we're counting back from the decimal places, that will tell me the negative exponent. And then we know log to the 0 is not possible. Now this is a good question. So why is log to the 0 not possible? Well, if I put a base of 10, set it equal to x, I can claw it and I get 10 to the x equals 0. And we know this is not possible because if you raise, well, the easiest way is to go back and think about our exponential equations, right? They're asymptotic with the x-axis, so they're never going to touch. That's one way of doing it. Another way of looking at it is that if you play with plugging in numbers, if you plug in negative numbers, as we did earlier here, right? You get 10 to the negative 1 is 1 over 10. So if you do 10 to the negative 2, you get 1 over 100. So that's illustrating this trend that we're getting closer and closer to the x-axis. And if you plug in 0, you get 1. That would be this value here, right? And then afterwards, it's just shooting up, right? 10 squared, 10 cubed. So you can see if you plug in numbers, it'll never get to 0. So this illustrates an important aspect of log functions. The argument, which is the value, the log of what, has to be greater than 0. So if I say this argument is called a, it has to be greater than 0. So that is not possible. This has no solution. Okay. And this is apparently just a blank page. Okay, let's keep going. All right. The other component that is important here is sometimes you're going to see ln x. And all ln x means is log base e to the x. Okay. We like to use the natural log because of some of the properties that it has, and we saw that last time. So this is, if you're confused by any of this, don't let the notation confuse you. This is all that we're saying. I sometimes just rewrite it as such, just to illustrate what each of these are saying. Well, this last one's going to take a little more work. Okay, so we said earlier, right, 1 is the same thing as e to the 0, right? So this makes sense that the first one is true, because if the bases match up, it's the exponent, right? So that's how I would look at this one. This one here is just, again, what's the exponent? It's 1, so this is 1. What's here? The exponent is x, so this is x. Okay. 4, we said, let me put it this way. We made the argument that when these match up, we can just say those go away, and then we're left with just x equals x. And that's okay. So if we look at this here, this should be apparent that this is 3. If it's not, remember this is the same thing as this. When these match up, it's the exponent. If you're not seeing, then we'll write it as e, log base e. 1 over e to the 4th is the same thing as e to the negative 4th. So realize this means this. This is just a fancy way of saying reciprocal. So again, when these match up, it's just the exponent, negative 4. And this is, again, what you want to do is you want to rewrite it in a way that makes sense to you. So we said, if you don't see this, all right, we're saying e to the x equals 0. Remember, e is just a number. We said last time we know it's roughly 2.7. So think of the graph, right? And this thing is never touching the x-axis. Hence, this does not exist, or the empty set. Okay. This one, so here's where you actually start getting into an issue in terms of you can't do a question like this by hand. Okay. So natural log of 10, you just can't do it by hand because it's just e to the what? I mean, we can say this is e to the x equals 10, but there's nothing else I can do with this. If I say it equal to x, you can claw it and get this, right? But there's nothing more we can do with that by hand. So I'm going to just leave that as natural log 10. This one here, right, when these match up, they can go away, and you're just left with pi. 6, express the equation in exponential form and find its domain. Okay, so I'm going to start off with what the domain is. We said this argument, this value here has to be greater than 0, so x minus 1 is greater than 0, which means x is greater than 2. Another visual representation of this is that the parent function of the log looks something like this. It's a general shape. And it has a vertical asymptote at 0. So if we say minus 1, what happens? The vertical asymptote shifts over 1. Okay? And so that kind of tells you that this thing is approaching one. I just said 0 plus 1 is 2. Yeah. Okay. And this is, but this, what's really awesome about what just happened and why I didn't edit this out is, and this is what you're seeing, is that when you think in multiple ways, you catch your mistakes. So don't just think algebraically, think graphically. Don't just think graphically, think algebraically. What I always like to say is Precal is about drawing the pretty picture to see what's going on. Okay, so if the question was, what is the domain of this? The domain of that would be, it's got to be greater than 1. Okay, now let's actually solve it. So we are given this is natural log x minus 1 equals 4. Let me double check. Okay. Again, what my recommendation is, if you struggle with this in any capacity, rewrite it as a log base e. So we have it like such. We can claw it, and we'll get e to the 4th equals x minus 1. And then we're going to solve this by adding 1 to both sides. And e to the 4 plus 1 is x, which is satisfactory. You can leave the answer as that. Remember, e is a number. I could calculate this out. But it's just e to the 4th plus 1. Okay, so if we have something like this. Now, there's two approaches to this. We can claw it, and we get log base e, right, to the 0.5 equals x plus 1. I froze there. And then we could move everything over, subtract 1, and we could leave it as such. Or, if you wanted to, you could take the natural log, I'll use this natural log here, the natural log to both of the sides. So it's e to the x plus 1 is 0.5. If you take the natural log of both sides, right, we know that this is going to cause this to go away, and it becomes x plus 1 equals natural log 0.5, and then subtract 1. And both of these are saying the same thing. So, I got 30 seconds left. This is just x squared minus 9 is greater than 0. I'll leave it to you to solve that. And that's it. Okay. So, well, yeah, I'll leave it to that. So, there you have it. So I hope this makes sense, and I will catch y'all in the next math video.